Okay, recording has started. Fine. So, an Orifice Meter. Okay, there are. I have told you that there are three Venturi. Sorry, there are three we are using to calculate the flow rate. That are Venturi meter, Orifice meter, pitot tube, and one more is notch and weirs. Okay, notches and weirs. Okay, so we will go with the next flow rate flow measuring device, that is Orifice meter. Orifice meter is used to measure the rate of flow of a fluid which is flowing through a pipe. It is having the same definition as that of the Venturi meter. So Venturi meter is also used to measure the rate of flow or discharge, and we are also using Orifice meter to measure the rate of flow. Okay, it is a cheaper device as compared to the Venturi meter because its construction is very simple compared to the Venturi meter. It also works as the same principle as that of the Venturi meter. It is working on the basis of same principle as that of Venturi meter. So these Orifice meter, Venturi meter, and Pitot tube are used to measure the flow rate of the fluid which is flowing through the pipe. So it consists of a circular shape, flat circular plate which has a circular sharp edged hole called as orifice, which is concentric with the pipe. So it means that if there is a pipe, okay, so we are placing a orifice. Okay, this orifice is having a this circular plate is having a orifice which is in concentric with the pipe. If this is the center of the pipe, and the orifice center of the pipe will be concentric to it. Concentric means having the same centers. Both the circles have the same center. So whatever fluid, if this is a pipe, okay, so this is a pipe, okay, I am placing, it consists of a flat circular plate with a circular sharp edged hole. Okay, so we are placing a plate like this, and it is having a hole here like in this area. Okay, and it is concentric. It is concentric to the center of the pipe, and this hole is concentric to the center of the pipe. Okay, and this is the plate, this is the hole here. Okay, imagine from front view, from the side view it is, from the front view it will look like this. Okay, this is the hole. Okay, this is the pipe in which I placed a circular plate and which has a hole. Okay, then, or also known as an orifice, that's why it's called as Orifice meter. And this orifice center and the center of the pipe is concentric, means they're lying on the same center. The orifice diameter is kept generally 0.5 times diameter of the pipe. So whatever orifice diameter is there, whatever circular plate, if we have inserted in the pipe, whatever orifice it is having, okay, this is the orifice, this is the circular plate, and this is the pipe. If we consider, then the diameter will be 0.5 times that of the diameter of the pipe. So 0.5 times of diameter of pipe, dp. Okay, so it may vary from 0.4 to 0.8 times the pipe diameter. Okay, so the orifice will be having less diameter compared to the diameter of the pipe. A differential manometer is connected.
Sir, one student is
What
waiting
happens?
to join.
Wait. Okay, fine. Okay. So a differential manometer is connected at section 1 and 2. So I'll show you the diagram in that you can understand how it is. But you understand that there is a pipe and we are placing a circular plate in this, and this circular plate is having a orifice over here. If I consider this like this. Okay, if you see it from the side view, this is the pipe diameter. This is the circular plate and it is having a orifice like this. Okay, and this center of the orifice and the center of the pipe is concentric because they lie at the same center. Okay, so a differential manometer is connected at section 1, which is at a distance of about 1.5 to 2.0 times the pipe diameter upstream from the orifice plate, and at section 2, which is a distance of the half the diameter of the orifice and the downstream side of the orifice plate. So one manometer will be connected here, another manometer will be connected here at some distance, which is shown here. Okay, I'll show you the diagram next in the next slide so that you can understand. So this is an orifice meter. So the fluid is flowing in this direction. The direction of flow is like this. This is a pipe where I have placed a circular plate which is having a orifice. This is the orifice part. Okay, so what happens is whenever the fluid comes like this, what will happen? It will deflect here. At this point, it will deflect and pass out, because this is the only place or space through which the fluid can come out. Okay, through which the fluid can come out. So you can see that where the differential manometer is connected. At one is connected before the orifice plate, another is connected after the orifice plate. So that is shown like 1.5 times of distance from before the orifice plate, and 0.5 times after the and after a distance of about half the diameter of the orifice plate. Okay, like this it is. You can see the pipe, and we are placing a circular plate to it, which is having a orifice. Orifice means a kind of space through which the fluid can flow. Okay, so to which we are connecting a what? Differential manometer. So you can see that the pressure is changing over here. So if this goes dip, if this goes below, then it means that the pressure of whatever fluid is flowing through the pipe will be more compared to the pressure of fluid which is coming out of this. And at this point, you can see that the pressure is less. That's why there is a difference in the manometer, differential manometer. Okay, so this is a bit quite different from the what? Venturi meter. But in Venturi meter, we are making the shape like that. We are making the shape as if it is like this. We are having a converging. This is the throat, and there is the divergent part, which is connected to the pipe. Right? You can imagine that this is the pipe inlet. This is the throat, because the area is reduced over here. Right? The area is reduced over here. Same way in the throat, which is happening in the Venturi meter, here also the area is reduced, and again it is deflected back. Okay, it is diverging. Here it is converges at this point, and here it is diverging. Okay, so see here, this is converging part, this is throat, and this is diverging. That's why we are telling that it is having the same principle as that of the Venturi meter, but the way of deriving is a bit different. Okay. Okay, so let P1 be the pressure at section 1, V1 be the velocity at section 2, A1 is the area at section 1, and P2, V2, E2 are the corresponding values at section 2. So this is the pressure, velocity, and area at section 1 at this point. Excuse me. Okay, and P2, V2, and E2 are the corresponding values at section 2 here. Okay. Now we apply the Bernoulli's equation at section 1 and 2. What is the equation for Bernoulli's equation? Anyone? What is the equation for Bernoulli's? What is the equation for Bernoulli's? Anyone? V1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g, V2 square by 2g plus Z2. Okay, this is an expression. Now, so I have written it like this: P1 by rho g plus Z1, P2 by rho g plus Z2 equal to V2 square by 2g minus V1 square by 2g. I have separated this. Now, what is this? This is H. That is P1 by rho g plus Z1 equal minus P2 by rho g plus Z2 equal to H. Okay. Now, therefore, H equal to what? If this is completely H equal to what?
Sir?
Yeah.
Sir, give some time to note down, sir.
Okay, you want time to note down. But when I explain it, you can just, I will send the notes now, then you can just practice it. That was my point. Is it fine? Because if you go on noting it down, it will take time. That's why. Is it fine, or should I keep it? Shall I continue?
So send the notes.
Sir.
I'll be sending the notes. Okay. First you listen how it works, then you can have the notes. I've already sent the notes for Venturi meter till Bernoulli's equation. I have to send for Venturi meter and Orifice meter. Okay. Fine. Okay, P1 by rho g plus V1 square by 2g is the Bernoulli's equation. So P1 by rho g plus Z1 minus P2 by rho g plus Z2 equal to V2 square by 2g minus V1 square by 2g. So we know that this is H. H equal to V2 square by 2g minus V1 square by 2g. Yes. Okay. Now, P1 by rho g, this one is H. Therefore, H equal to V2 square by 2g minus V1 square by 2g. Now we have taking everything in terms of V2. Okay. V2 square. So V2 square equal to, this is common, 2gh. We'll take it this side. 2gh equal to V2 square minus V1 square. So V2 equal to square root of 2gh plus V1 square. V2 equal to square root of 2gh plus V1 square. So this will go here. V2 will come this side. So V2 square equal to square root of 2gh plus V1 square. Now this is the equation 1. This is the equation 1. Okay. So you have applied the Bernoulli equation at both section 1 and 2 in that Orifice meter. So the equation is like this. So we are taking, as we know that we have seen in the value of h. Okay, h is equal to P1 by rho g minus P2 by rho g. Okay, why Z1 and Z2? If I don't take this, because when I won't consider them when Z1 is equal to Z2. Okay, that is the pipe is horizontal. And the pipe is horizontal, we are taking Z1 equal to Z2. That's why it will be P1 by rho g minus P2 by rho g. So this will be H. That H will be equal to V2 square by 2g minus V1 square by 2g. Okay. This is the equation 1. Next. Now section 2 is at the vena contracta and A2 represents the area at the vena contracta. If A0 is the area of the orifice meter, then so whatever section 2 we have found out, this is the pipe and this is the orifice plate. Okay, this is the orifice. Okay, and this is section 1, this side. Okay, this is section 1. This is section 2. So this section 2 is the vena contracta. Why vena contracta? Because at this point the fluid is getting contracted. At this area the fluid is getting contracted and getting diverged. Okay, and A2 represents the area at vena contracta, because at this area, this is A2, this is A1. So A2 represents the area of the vena contracta, because the fluid comes like this and diverges. Fluid comes like this and diverges. Therefore, at this point, this area is called as vena contracta. Okay. If A0 is the area of orifice meter, then we have, if we place the A0 as the orifice meter area, then we have Cc equal to A2 by A0. Cc means this is coefficient of contraction. Cc means coefficient of contraction. So A2 is the area after the orifice and A0 is the area of the orifice meter. So the ratio of this is nothing but coefficient of contraction, where Cc is the coefficient of contraction. This is one more term which you are getting. There are two more terms, like we have discussed in Venturi meter, there will be coefficient of discharge Cd. And here we are getting coefficient of contraction and one more term, that is coefficient of velocity. Okay. Done. Now A2 can be written as A0 into Cc. That is A0 is area of the orifice meter, then Cc is the coefficient of contraction. By continuity equation. What is continuity equation? Can anyone tell me? What is continuity equation? What is coefficient of contraction? Sorry, continuity equation. Anyone?
Q is equal to A1 V1.
Q is equal to A1 V1. It is A1 V1 equal to A2 V2. Q is equal to A1 V1, it's discharge. Okay. But continuity equation is what? A1 V1 equal to A2 V2. Therefore, we'll keep it like this. A1 V1 equal to A2 V2. Now, V1 equal to what? A2 by A1 into V2. Now substitute the value of A0 into Cc here in A2. So you will get V2, that is equal to A0 into Cc divided by A1 into V2. This is your equation 3. So equation 1 is what? V2 equal to square root of 2gh plus V1 square. This is equation 2 and this is equation 3. A0 Cc divided by A1 into V2. Now, what we are doing, substitute this value of V1, substituting the value of V1 in equation 1. So, what is the equation 1? V2 equal to 2GH plus V1 square. Equation 1 is V2 equal to square root of 2GH plus V1 square. So, substitute the value of V1 here. It will be A0 square, Cc square, A1 square and V2 square. So A0 square, Cc square, V2 square divided by A1 square. This is our equation 1 in which I have substituted the value of V1. Understood? So there are three equations which we have got and we have found out this, the value of V2. Now we have to simplify this. V2 square equal to 2GH plus A0 divided by A1 whole square into Cc square into V2 square. So I have just simplified it. Okay, I have taken V2 square root kana. So this square root I have taken out and it will become V2 square. V2 will become V2 square. So it will be 2GH plus A0 by A1 square whole square into Cc square into V2 square. Okay, now V2 square equal to what? V2 square. Here also V2 square is there. Here also V2 square is there. I can take a common. So what I'll do, I'll shift this here. So it will be 1 minus, when it comes this side, it will be V2 square minus this A0 by divided by A1 whole square, Cc square, V2 square. So when I take this outside like this, if you understood it, V2 square minus A0 by A1 whole square, Cc square into V2 square equal to 2GH. I have taken this whole term here because V2 is common over here. So when I take V2 as common, what will remain? So when I take V2 as common, V2 square as common, so it will be 1 minus this A0 by A1 whole square into Cc square equal to 2GH. Now what will be the formula for V2? V2 will be square root of 2GH divided by square root of 1 minus A0 by A1 whole square Cc square. So you understood how this is, thus we have got. So the first equation was what? I have substituted the value of V1 in V2. So we got this equation. It was like V2 square root of 2GH and everything. I have taken this out and then I have done it like this. Okay, so it's to simplify it in an easier way. Fine. So V2 equal to square root of 2GH square root of 1 minus A0 by A1 whole square into Cc square. Now can we find out discharge? What is the formula for discharge here? Q equal to A2 into V2. Now substitute the value of A2 and this is the whole V2. So what will be the equation? A2 into okay, so we'll see here what we have to do next. Q equal to A2 into V2 equal to V2 into A0 Cc. V2 into A0 Cc. Right? Because A2 was A0 into Cc. Now substitute this value here. So it will be like this. Q equal to what is A2? A0 into Cc into square root of 2GH. A0 into Cc into square root of 2GH. Then square root of this. Okay. So what I have done is I have changed A2 as A0 into Cc and substituted here. Okay. Now we have to get the final equation for discharge. So this expression is simplified as follows. So whatever now we are doing, it is for theoretical discharge. We want the actual discharge also. Okay, this is the equation for which we have got by substituting in Q. Okay, now so above expression is simplified by using this formula. CD equal to Cc square root of 1 minus A0 1 square whole square square root of 1 minus A0 1 by A square Cc square. This is why, because CD equal to CC into CV, where CD is the coefficient of discharge, CC is the coefficient of contraction, and CV is the velocity coefficient or coefficient of velocity. So using this, so it is CD equal to CC into CV. So CV value is this. Velocity, actual velocity by theoretical velocity. CV matlab. Okay. And CD I have told you it is Q actual by Q theoretical. Okay. So both are there here. So now, so how can we write? Now I have taken everything in terms of CC. So CC you take, you multiply it with CD and you divide it by this one. So it will be interchanged. Okay. Then you substitute this value of CC in equation 4. Substitute the value of CC in equation 4. Okay, we are substituting the value in equation 4, whatever value we had got previously. So in equation 4, if we substitute, we get this expression. So when we simplify this expression, can anyone tell me what will be the expression for this? Can anyone tell me the final expression? See, what will get cancelled? This one and this one will get cancelled. So what will remain now? A naught CD square root of 2GH divided by what? Square root of 1 minus A naught divided by A1 whole square. This is your Q. Okay, done. Can we further change this formula? The further it can be simplified to this expression. CD equal to A naught into square root of 2GH divided by square root of 1 minus A naught by A1 whole square. Now it can be further brought like this. CD equal to A naught square root of 2GH. A1 क्या होगा? A1 minus A naught whole square divided by A1 square. If I take this out, what will happen now? See this one. 1 minus A naught square divided by A1 square. Do you agree? This will be square root. So if I take this here, so A1 square minus A naught square, this will be square root divided by A1 square. Okay. When I take out this square and this square root and square, it will be A1. And I'll take it into the numerator. CD equal to A naught into A1. This A1 we have got from the denominator, from this one, into square root of 2G divided by square root of A1 square minus A naught square. So this is the final expression for discharge through the Orifice meter. Okay. Any doubts? Shall I derive it again?
Yes, sir.
I'll repeat it 1 second for you. Okay. So this is a bit confusing derivation and also important from the exam point of view. So Orifice meter is having the same principle as that of a Venturi meter. So Venturi meter used to have a converging part, a throat, and a diverging part. Same way here. So the fluid is converging over here. It is diverging at this point. So we can take this as a throat. So it is having the same principle as that of the Venturi meter. Right. Now, P1, V1, A1 are the pressure at section 1 and pressure at section 1. P2, V2, E2 are the corresponding one to the section 2. Apply Bernoulli's equation to this. So when you apply Bernoulli's equation, the equation is like this. Done. So this complete, whatever we have got, this complete is nothing but H. H equal to V2 square by 2G minus V1 square by 2G. Then we are taking in terms of V2. So V2, this is the equation 1. V2 equal to square root of 2GH plus V1 square. So next what we do is we calculate we say that whatever area is there after Orifice, that is called a Banach contract, and that is represents the A2. If A0 is the area of the Orifice meter, then we have CC equal to A2 by A0, where CC is the coefficient of contraction. So A2 is the area of the orifice, sorry, area after the orifice meter or area after the orifice, and A0 is the area of the orifice meter. Whatever hole we have given in that orifice, that is whatever orifice area is there, that is A0. So where Cc is the coefficient of contraction. A2 equal to what? A0 into Cc. This is our equation 2. Now by continuity equation we are giving A2 V2 A1 V1 equal to A2 V2. But V1 equal to A2 by A1 into V2. We are taking A2 in terms of like A2 as A0 Cc into V2 divided by A1. A0 Cc divided by A1 into V2. This is our equation 3. Now substituting the value of V1, this whole, in equation 1. So in equation if we substitute V2 equal to square root of 2gh plus V1 square. I have to substitute here. Okay, so when I substitute this, so I have to substitute the whole. A0 square, Cc square, V2 square divided by A1 square. After substituting, we are simplifying it to V2 equal to square root of 2gh like this. Okay, V2 equal to square root of 2gh divided by square root of 1 minus A0 divided by A1 square, Cc square. But discharge is what? Q2 equal A2 into V2. But A2 is what? A0 into Cc. So substitute the value like V2 will be remain A0 into Cc into this expression. Okay. So A0 into Cc, V2 complete. Done. After substituting, we are getting equation 4. After equation 4, we are simplifying it to using this value, that is Cd into Cc, because I want this value, what is meant by Cc. Okay, so as Cc is very small, it is very negligible, coefficient of contraction is negligible, so we are going for the value of Cd. So Cd equal to Cc into Cv, so we are getting like this. Cv is V theoretical by V actual by V theoretical. V actual by V theoretical, Cv. Okay, so that is the formula which we have got. We are getting this. We have taken, I have taken Cd and Cc. I have just interchanged Cd and Cc here. So we have got the expression like this. I am going to substitute Cc in equation 4. In equation 4, I am going to substitute. When I substitute, I get this. This and this will get cancelled. It will remain as A0 Cd into square root of 2j divided by square root of 1 minus A0 1 by A1 whole square. So this is remaining. So I will take the LCM at this point. I will be remaining with A1 on the top numerator, and denominator it will be square root of A1 square minus A0 square. This is the final expression for Orifice meter discharge. Okay, CD equal to CD into A0 into A1 square root of 2j divided by square root of A1 square minus A0 square. Okay. Now we'll see the difference between the Venturi meter and Orifice meter. So when we are going to use Venturi meter and when we are going to use an Orifice meter, because both are having a similarity that they measure the rate of flow or discharge. So the losses are very less, hence the value of CD is high in Venturi meter. So here the losses are less, that's why we are getting a value of 0.98. But for an Orifice meter, it will be around 0.6 something, 0.6 to 0.65 to 0.7. You will be getting the value of CD. So the losses are more here, because whenever the fluid contracts, and it will contract near the that orifice and it will expand, right? So at this point there is more formation of eddies. So eddies formation causes the loss of energy of the fluid which is flowing. Okay. It cannot be installed where space is limited. It requires less space. Orifice meter requires less space. As I have told you that Venturi meter is costly to install and replace, but Orifice meter is easy and less costly. Okay, done. It is used for the main difference is that we are using Venturi meter to measure the high flow rates, but for Orifice meter we are using for moderate and low flow rates of flow. Okay, so these are the differences between the, or comparison between the Orifice meter and Venturi meter. So next one is the problem. Okay. So the problem is based on, okay, an Orifice meter with orifice diameter 15 centimeter. An Orifice meter with orifice diameter 15 centimeter is inserted in a pipe of 30 centimeter diameter. So there is a pipe of 30 centimeter diameter and a orifice is inserted into this. And this is the diameter of the orifice. 15 centimeter, and this is the diameter of the pipe, 30 centimeter. The pressure difference is measured by a differential manometer on two sides of the orifice meter. One side is this, another side is this. We are measuring the pressure difference using the mercury differential manometer. Find the rate of flow of specific gravity of 0.9 and the coefficient of discharge of the orifice meter is 0.64. Okay, so which fluid is flowing through the pipe? Can anyone tell me which fluid is flowing through the pipe? Which fluid is flowing through the pipe? So here specifically has written that it is a mercury oil differential manometer. So it is the oil which is flowing through the pipe. And we have to find the rate of flow of oil, which is having a specific gravity of 0.9. For this, the diameter of orifice is given as d naught equal to 15 centimeter. We have calculated its area. Diameter of the pipe is given as d1 equal to 30 centimeter. We have calculated its area. Specific gravity is given as s naught equal to 0.9. The CD is given. Okay. So what is the formula for discharge for an orifice meter, which we have seen in the previous class? This is the formula. So CD equal to A naught into A1. CD equal to A naught, sorry. Q equal to CD A naught into A1 divided by square root of 2GH. Wait. Q equal to CD A naught into A1 divided by square root of A1 square minus A2 square into square root of 2GH. This is the formula. Now, from this, what all values we have with us? Anyone? Everything is in terms of centimeter. Later, if you want, you can convert it into meter, or you can keep it like this. Measure its value in cube, that is centimeter cube per second, convert it into liter per second. So we have the value of CD. What is the value of CD given? What is the value of CD given over here? 0.64. We have the value of A naught, that is 176. We have the value of A1, that is 706. A1 square and A2 square is also given. That is nothing but that only. A naught minus A1. A1 minus A naught square. A1 minus A naught square is given. The value is given into square root of 2. 2 is a constant. G is 9.81. So H we know how to calculate. That is, he is given the specific gravity. He has given the specific gravity of the oil. So H equal to X is the change in the differential reading, differential manometer reading, that is 50 centimeter. 50 divided by 50 into specific gravity of mercury is 13.6, oil is 0.9 minus 1. We are getting 705.5 centimeter of oil. Now substitute all the values and find the answer for this. If you want the formula is this one. Q equal to CD A naught into A1 divided by square root of A1 square minus A naught square. Okay, into square root of 2GH. This is the formula. This square root is for the whole term. Can anyone tell me the answer for Q? What is the answer for Q? Substitute the value now. CD is 0.64. A naught is 706.85 into 176.7 divided by square root of 706.85 whole square minus 176.7 whole square into square root of 2 into 9.81 into 705.5. As I have told you that G value is 9.81 meter per second when it is in meter. Okay. But in centimeter per second, centimeter per second square, it will be 981. Right? So substitute and let me know the answer first. What is the answer Q? Yeah. 10⁻3. What is the unit? Everything is in centimeter. So centimeter cube per second. Not how it will be meter. Everything is centimeter. Na? So remember that discharge unit is meter cube per second. If we are calculating in terms of centimeter, it will be centimeter cube per second. Okay. That is centimeter cube per second. So 137,414.25 centimeter cube per second. If we convert it into liters, that is 137.414 liters per second. Okay. Fine. Any doubts? Okay. So next problem has to be done by you people. So the question is that in an Orifice meter with orifice diameter of 10 centimeter is inserted in a pipe of 20 centimeter diameter. Okay. So diameter, orifice diameter is 10 centimeter. Diameter of pipe is 20 centimeter. The pressure gauges fitted upstream and downstream of the orifice meter gives a reading of P1 equal to 19.62 Newton per centimeter square and P2 equal to 9.81 Newton per centimeter square respectively. Coefficient of discharge is CD is 0.6. Find the discharge of water through the pipe. Now here what we require, we know the formula, we need to calculate Q. Okay. So what is the formula for Q? Q equal to CD A naught into A1 divided by square root of A1 square minus A naught square into square root of 2GH. Okay, this is the formula. Now, what all things we have from this? Can anyone tell me? It is a bit different from the previous problem. A bit different. Everything is same. Procedure is same.
A1 we have.
A1, A naught, we have that, because if we have D naught, we can calculate A naught. D naught है तो A naught है, D1 है तो A1 है, because pi by 4 D square diameter. Then what we want? We have G, that is 981 centimeters per second square. Okay. Then we want H. How you will calculate H? Which formula you will use? Which formula you will use? Which type of fluid is flowing through the pipe? Has he given? He is telling that find the discharge of water. We just know that it is discharge of water. So in manometer it will be what?
Water,
manometer will be having water. Okay, sorry, it is water. The water is flowing through the pipe. Okay. Now, which formula we can take to calculate H? if I go for the previous problem, that is H equal to X into Sg by S0 minus 1. Okay, will it be applicable over here? If I go for the
No,
previous problem,
no, sir.
if I go for the previous problem, can I apply this equation here? In this, can I apply this equation? I cannot apply this equation because they have not given Sg, S0 and X. S0 we know that is 1000. It is common. S0 is 1. Okay, that is water. We know that. But they are not given the value of Sg and X value. Sg भी पता है क्योंकि mercury है. We can take that as 13.6 divided by 1 minus 1. Okay, but they are not given the reading of differential manometer, that is X. Okay, so we cannot take this expression. But which formula I can take to calculate H0? Which formula I can use? Tell me fast.
Q actual. Discharge.
Very good. How can you use discharge to calculate H? Man, you have to calculate discharge and first you have to find H, then you can calculate discharge. Na? Okay. So someone has said P1 by rho G minus P2 by rho G. See here, the question is like this. Listen to the question first. So there is an Orifice meter which is having 10 cm and 20 cm. This is area E1 and A0. The pressure at one is 19.62, pressure at another is 9.81. The coefficient of discharge is 0.6. Find the discharge of water flowing through the Orifice meter. The equation is like this. I'll write the equation first. CD into A0 into A1 divided by square root of A1 square minus A0 square into square root of 2GH. Do you agree with this expression? Do you agree with this expression? This is the expression to calculate rate of flow. Now, in this we can calculate A0, we can calculate A1 using the diameters. Okay, then can we calculate H? For H we have to use this formula, H equal to X, Sg by S0 minus 1. We have this, we can easily say that it is 13.6 divided by 1. But we don't have X value. This is the reading of differential manometer. Here not given. Now how to find out the value of H? So someone had said me that the value is P1 by rho G minus P2 by rho G equal to H. By using this formula we can find out because they have given us the value of P1. They have given us the formula value of P2. So both the values are given. So we can determine the value of what? H. Okay. Now you calculate the value of P1 by rho G first. P1 by rho G equal to P1 is how much? 19.62 into 10 raised to 4 divided by rho G is 1000 into 9.81. Calculate what is the answer. First you calculate A1 and A1 diameters. How much you got diameter A0? Anyone fast? Diameter A0. A pi by 4 into 10 to the square.
7.8. 8.53.
78.53.
Centimeter square. Okay. A1 pi by 4 into 20 square. Pi by 4 into 20 square.
314.5.
314.5. Okay, 15. Fine. Now you calculate this P1 by rho G and P2 by rho G. If you have kept it as centimeter itself, you can keep this everything in terms of centimeter only. Okay, you don't have to multiply it with 10 raised to 4. But if you don't multiply, what will happen? This rho is in terms of meter and this G is also in terms of meter. So better what you do, you convert it in terms of meter first. You get the answer in terms of meter. Then we'll see what to do. 9.81 10 raised to 4 divided by 1000 into 9.81. What is P1 by rho G equal to?
Sir,
H
100.
is equal to 10.
H equal to 10 what? Unit centimeter.
20. 20.
10.
What is P1 by rho g first? You tell me P1 by rho g.
20.
20.
20 meter of water. 20 meter of water, because you have taken everything in terms of meter. This will be P2 by rho g.
10.
10 meter of water. 10 meter of water. Now you have got both. So what is H? P1 by rho g minus P2 by rho g. 20 minus
10.
10 equal to 10 meter of water. Okay. Now I have taken everything in terms of centimeter. So just convert this 10 meter into centimeter. How much it will be?
0.1.
Convert 10 meter into centimeter of water.
1.
Convert 10 meter equal to centimeter of water. 1 meter equal to 100 centimeter, right? So what will be 10 meter equal to? 10 into 100, right or no? You know conversion or no? See here, listen. 1 meter equal to 100 centimeter. Do you agree with this? Okay. Next is 10 meter of water. 10 into 100 divided by this. It will be what? 1000 centimeter of water. So it will be 1000 centimeter of water. So you got the value of H now. Can you calculate the discharge? Can you calculate the discharge and tell me the answer? Q equal to CD A0 into A1 divided by square root of A1 square minus A0 square into square root of 2GH. Now you have to substitute the value of G as what? How will you substitute the value of G? 981, huh? 9.81.
$9.81.
No, 9.81 is, see here, listen. 9.81 is 9.81 Newton per, sorry. 9.81 meter per second square is the unit. Sorry, it is acceleration due to gravity G. But as we have taken everything in terms of centimeter, this will be 981 centimeter per second square. That's why I'm telling you, if you are converting one thing, everything into centimeter to meter, convert it. Otherwise, keep a centimeter and do the calculation. But you should not get confused over here, because there is a confusion with one point and your answer will be wrong. (6817.24 cubic meter per second). Okay, convert that into liters per second. 68.17. Good. The answer is correct. The answer is correct. Okay. 68.17 liters per second is the answer. Understood? You should not get confused with the conversion centimeter to meter, meter to centimeter. That's the point. If you are taking everything in terms of centimeter, take in centimeter. If you are taking everything, if you don't want, नहीं चाहिए हमको, हम सब मीटर में रखेंगे तो, so not getting any confusion, you can keep everything in terms of meter. Calculate in terms of meter cube per second as discharge, and then you convert it into liters per second. Okay, done. Any doubts? Okay, so we have done with the Orifice meter also.